To converge or not to converge? That is the question we have here. And we start with this integral. Don't be fazed by this infinity symbol. It's just there to scare you. When in reality, it is as simple as writing a limit of a finite integral from 1 to t. So that is usually what they call an abusive notation. When you have something that simplifies the notation, but then what happens in end effect is that people do not understand what you were talking about in the first place, which is why abusive notation is not really welcomed in our tutorials. So I'll try my best not to abuse any notation, because you know abuse is a bad thing. So it makes sense to do that. So we are here with the integral. We want to compute the integral. Do you know what the antiderivative is? Because I do. I mean, otherwise I wouldn't be here, right? So let me rewrite this as 1 over x times ln of x. Do you see it? You don't see it? Okay, well that's completely fine. You know, there's nothing wrong with that. If you want to proceed with the integration by parts, you could of course do that to prove this, but in the end this will give us half of ln of x squared. Why is that? Well, it's very simple. Just bring down the power, take away 1, and then take the derivative of the inside function, which in this case is the ln of x. To be very precise, let me make this bracket. So bring down the power, take away 1, and then the derivative of the inside function is 1 over x. So that's why it works. If you do lots of integration by parts, you can see it very quickly. Anyway, so that's the integral of the function. And if you would like to assess whether this integral converges or not, then we need to simply take the limit. Let me expand this first. The first thing I'm going to do is I'll write this half on the outside. And what we have here, I have to plug in t once and then plug in 1 the other time. This is being squared. ln of 1 is 0. So what we have on our hands here is ln of t squared. And we're taking the limit of ln of t squared as t goes to infinity. Now ln is an increasing function. And if ln of t is an increasing function, then ln of t squared better be an increasing function as well, because it's a composition of another increasing function, which is x squared. ln and then x squared, both, you get ln of x squared. So this is clearly increasing. Because it is increasing, and we are taking the limit to infinity, then this diverges. That's about it. Maybe I'll do the integration by parts part here, if you're interested. If you're not, you can of course close the video. I made a horrible mistake, which is not to write dx. Big mistake. I hope they don't fire me from this AA position. Don't forget to write the dx, otherwise the integral doesn't have any meaning. Okay, I'm glad I didn't end the video there. So I don't know how to integrate ln of x, so I'll choose it to be my u. I'll choose this to be dv. And then I'll write this as uv minus the integral v du. So that's how it works. I get ln of x times the integral of 1 over x, which is ln of x. Right, so if you take the derivative of ln of x, you get 1 over x. And then v is ln of x again. And then this derivative is 1 over x. That's literally what we were talking about. It's the function and its derivative, basically. I feel like this could have been done using integration by substitution. It should be possible. I mean, it's not a mistake, because here's the thing, because the derivative is going to be 1 over x dx, and then we get the same integral again. So I want to be very precise here. We get the same integral here and there. So in principle, twice of our integral, if I add this to both sides, is equal to well, ln of x times ln of x, which is ln of x squared. So if you divide by 2, this is your antiderivative. You could, of course, proceed with integration by parts. I don't know how sorry, my apologies. With integration by substitution, just choose u to be equal to ln of x. Then the derivative cancels out. I don't know how I didn't notice that. I guess I'm just hardwired to use integration by parts for every single problem. And that's not a healthy way to move forward. I'll try to be more considerate of the other integration techniques we have, because it is important to be considerate, especially when it comes to to integration techniques. So that's about it. I don't think there's any need to spend more time on this. This is it.